morning, everybody. As he said, I'm Patrick Reynolds. On GitHub, I am at Peaky. I'm going to talk today about what the systems team does at GitHub, which is scale Git to the size of the biggest Git host in the world. How we run our GitHub repository file servers so that we can host host huge numbers of repositories efficiently and reliably at scale. So the motivation here, GitHub is big. GitHub's got about 35 million repositories, about 30 million gists. It's growing fast. We execute some form of Git or libgit2 over 1 billion times a day on those repositories. And in spite of all that, GitHub needs to be fast, it needs to be reliable, it needs to be consistently fast. So, for example, our 99th percentile page load times on the website are about half a second, which means a lot of those page builds, they go to Git repositories. They're calling Git, they're shelling out to Git, or they're hitting libgit2, the library. And so to get that page built in half a second, those repository touches, they need to come in well under half a second, at least 99% of the time. And in addition to this, when you've got 35 million repositories, you see a lot of corner cases. We see really big repositories. We ask people to keep the repositories under a gig. Sometimes they go over 40 gigs anyway. We reserve the right to lock them, but sometimes people do it. We've got some very deep commit histories. We've got repositories that go back 20 years, which obviously predates Git. So you look in the history and it's CVS for a while, Subversion for a while, Git for a while. I'm glad they converted. We've got repositories that go back 500,000 commits. Linux is one of them. It's not the only one of them that's got a history that deep. Git log, Git blame are pretty expensive when you've got a history that deep. We've got some repositories with as many as 1 million branches and tags. We've got repositories with high push rates. So we've got some repositories that push 10,000 times a day, effectively using GitHub as a log file. Just every 5 seconds or so during the business day. And then we've got some public repositories too. We've got a public repository with 80,000 forks. We've got a public repository that routinely gets requests from 100,000 different client IPs. I'll get a little bit more into that last one later in the talk. So the rest of this talk, I'm going to talk about how we run Git at scale, and that breaks down into 4 things. One is Git itself has to be fast. If you double the speed of something in Git, then you've doubled the amount of repositories that you can run on your servers. So any improvement to Git has a huge impact, both on the reliability of the site, the usability of the site, and how many repositories we can host. The second one, flip side of that, sometimes we have to slow Git down. The third, we call Git less. I'm going to talk about how we use caching. And then finally, and this is the Wired article that Chris mentioned, we keep now 3 copies of everything using a system we're introducing today called DGit, and I'll give you a little overview of that. So the first thing, this is our workflow for making Git fast. As I said, any improvement to Git has a huge impact to GitHub as a whole. We have to monitor. We have hundreds of repository servers. We monitor them with Graphite. We have alerts on a bunch of those metrics. So any server where the CPU is overloaded or it's running out of memory or response time is getting too slow, we get an alert, and that's really our first indication that something's gone wrong, that we need to go investigate. The second is triage. So once you know what server has gone wrong, some particular file server has too high a CPU load, or calls to Git core are taking too long now on that server, you want to find out what's actually happening on that server. So we log every single Git operation. Anytime we shell out to Git, we log to disk the repository, the command that was being run, the user ID, the client IP, and then performance things like how long did it take, how much CPU time did it take. So when a server starts to suffer for some reason, it's pretty easy to go in and say what on that server is consuming the most resources right now. If the server has been suffering for 5 minutes, you say look at the last 5 minutes. So logging everything, you uncover what the actual problem is. Then you have to recreate it. And so those logs that we keep have a very small amount of information about each request, because we get a lot of requests. But once we've narrowed it down to a problem, we can turn on more detailed logging. We turn on basically everything that the client sends us in the request so that we can replay it, capture it in a debugger, capture it in a profiler, and find out what's actually wrong, and then fix it, maybe. The rest of the talk is about what happens when we don't or can't fix the particular bottleneck. But our goal is to get any call to Git core under about a second. And that's a goal we don't hit 100% of the time, but we hit very close to 100% of the time. The rest of the talk is about that fraction of a 1%. When we fix bottlenecks in Git, we upstream them. So here is an arbitrary sample of bottlenecks that we've found and fixed. Often it's something that's quadratic. So it's something that takes quadratic CPU time in the number of references, or in the number of remotes, or in the commit history, or anything. And it's just a matter of finding that line of code and converting an array to a hash table or whatever. The biggest one here at the bottom, which is way bigger than converting an array to a hash table, was reachability bitmaps. This is something that VMG on the systems team at GitHub did based on work on JGit at Google. Google invented bitmaps. VMG wrote an implementation for the core Git, for the C implementation of Git. And you can see in the graph on the right, we started out, this is how long it used to take to clone the Linux kernel. It took about a minute. And after bitmaps, it took about a second. And so that's huge. That's very close to our goal of getting everything down under a second. It's 1.6 seconds of CPU time to clone the Linux kernel. And this made the file server, at the time one file server that we had hosting the Linux kernel, way happier. We use way less CPU. But we can't always make individual Git operations fast. Some of them are still going to be slow. And also, there are some that we just haven't made fast yet. We get new corner cases every day. We get new surprises. And so until we find a way to make that fast, or unless we can find a way to make that fast, we need to prioritize and delay Git operations. So there are two graphs here. These are old graphs, because the system I'm talking about here, we've had in operation for about 2 years. But on the left, this is CPU load on a file server. So the green, steady. And then boom, a bunch of requests for the same repo, basically identical requests for the same repo, come in, and suddenly the server is slammed. The blue line is that server's hot spare. Here, this is memory on that server, and red is memory mapped processes, and the bluish is block cache. Git servers are basically file servers. They need lots of block cache. So once that block cache gets squeezed out, this machine thrashes itself to death. And I don't know if those of you in the back can see it, but there's a little gap here. That's where the machine crashed. And here, I said the blue was the hot spare. That's where the hot spare took over. We used to get these pretty regularly. We would get a load spike, and we would lose a file server. And Gitmon is the system we built to fix that. And I'm going to talk a little bit about how Gitmon works. Gitmon sets limits for how much CPU, memory, and network any given user can use. They're really generous limits. It's basically impossible for individual developers, even a whole team of individual developers, to hit this limit. The only thing that hits this limit is scripts, and we've got lots of scripts hitting GitHub. Cloning for continuous integration, cloning to deploy to servers. Individual users don't impose that level of load. But we set these limits. We set them so high that almost nobody will hit them. Since people can hit GitHub without logging in, you can anonymously clone a public repository. We actually have buckets for per repository, per user ID, and per client IP. So this does a pretty good job of catching what we call the thundering herd problem, which is where a whole bunch of clients arrive and they want the same thing, or more or less the same thing at the same time, and the load spikes. These limits start out high, but we can adjust them automatically as needed. And so this graph here, the green is the CPU load on a typical file server. So it's reasonably healthy. It's about 10. And then a bunch of traffic comes in, and the CPU load jumps up to 20. It hits 30. We're starting to worry about impact on other repositories at this point, performance of any other repository on that file server, because we're hosting like 1 million repositories on that file server. And so the blue here, this is the percentage of quotas, the percentage of the original quota that's available to each user. So it starts out at 100, and it moves basically in inverse proportion to the CPU load. So when the CPU load gets high, we're down to about 40% of quota. And so the original generous quotas, they can come down to about 5% in order to keep the machines from tipping over. It's an emergency response, and it's very effective. Second thing we have to do, we have to predict the cost of each operation. So we need to know in advance this operation that we are about to allow, is it going to exceed the quota? Now that's, in the general case, it's impossible to predict the future. Gitmon has to model everything. It models per repository and per Git command. So for example, how long does it take to run pack objects on the Linux repository? 2 or 3 seconds. It models how long that'll take. And so when a request comes in, it looks up in that model, how long is it going to take, and will that fit under the current quota for that user, for that repository, for that client IP. And these models are long-term averages, so they're based on past behavior, and they're pretty good at they're good enough at predicting the future. And then any operation where the cost of that operation exceeds the available quota for that user, that gets delayed. Here's how that happens. Every time we start Git, every time we shell out to Git, it contacts Gitmon. And it tells Gitmon, the repository, the user ID, the client IP address, and the name of the operation. Gitmon is both our logging system and our priority load management system. And then Git sends the command schedule. And schedule is just a question, am I allowed to proceed? And Gitmon responds immediately with either continue, which means yes, it fits in the quota, go ahead, or wait. And if Git gets back wait, it sleeps a few seconds and tries again. And that's it. That is how you build a priority system, a load management system. That's how you prevent Git from tipping over file servers. Is sleep and then run schedule again, and that's a loop. Sometimes it has to wait more than once. And then finally, when after the Git process is allowed to proceed, at the end of the process, it sends how much CPU time, how much network I/O, how much disk I/O, and how much memory it used back to Gitmon to feed into the log, to feed into the model, so that we will know next time in even better detail how long that particular operation on that particular repository is likely to take. So here it is in practice. Here's how Gitmon works in the real world. It spreads out the peaks. So let's say we get 500 requests, each of which wants to take 5 seconds, all at the same time. And this is totally typical. We have customers that'll deploy a giant repository to 500 servers out in the cloud somewhere, and they all want to update at the same time. And depending on what they're fetching, it might take a few seconds of CPU on our file servers. You don't want to try to run 2,500 seconds of CPU time all at the same time. You're going to peg the server for 80 seconds. Nothing else will get done. You might even run the server out of memory. That was the graph we saw earlier. That really happens. What Gitmon does, it allows, basically, depending on the health of the server, it allows up to about 40 of those requests to come through at the same time. And as soon as they finish, another 40 come in, and as soon as they finish, another 40 come in. And so the whole thing, if they're cheap, they could fit in 5 seconds. If those requests are expensive, they could get spread out over 5 minutes. And they're kept, any individual user is kept at a load where they're not affecting the rest of the users on the machine. This is very effective at rate limiting while true loops. Now, I haven't seen our customers' code, but what I have seen is how it looks from our point of view, and there are definitely customers that fetch literally as fast as the network and the server will allow. Knock it off. If you're doing it, stop. But in a sense, now with Gitmon, it doesn't matter, because what happens is you definitely exceed your quota if you do this. And so some sleeps get put in on our side if you forget to put them in on your side. Also, you don't need to do this set up webhooks, but not everybody knows that. The other thing Gitmon does in practice, it's prioritizing everyone who's not exceeding the quota. So it's basically separating all the traffic on the machine into the 99% of people who aren't going above their quotas, who aren't using too many resources, who are sharing the machine nicely, and the 1% who aren't. And the 1% who aren't, they get through when there is capacity available. The most delayed user is us. We have 1,000 plus servers, and we deploy a really big repo to all of them. And we have some demand-side concurrency control. it doesn't always work, and so Gitmon steps in and says, you're going to make the server too busy, wait, and this works. I mean, it's not a big problem for your scripts to get delayed a few seconds, and so we're dog-fooding this one. Initially, we accepted ourselves from this. We exempted ourselves from these quotas, and then we said, why should we do that? Seems to work fine. The problem with this, with taking the thundering herds, with taking large batches of requests and making them slower, is it's a really bad experience for the customers whose requests are being made slower. It's fine for the other 99% of the users on that server, but it's bad for the customers who have made the 500 requests. And so we cache whatever we can, and we use memcached for things that we need to build web pages. We keep some longer-term caches on disk for things that are really expensive to compute. They're things that take 10 minutes to compute. And so we'll store them in the repository directory. But the main caching thing I'm talking about today is a new system we've built called Lariat. And the purpose of Lariat is to solve the thundering herd problem. So Gitmon mitigates the thundering herd problem. It protects other users from the thundering herd problem, but Lariat basically solves it. Lariat is a wrapper around pack objects. Now, pack objects is basically the back end of every fetch, pull, and clone. And Lariat wraps it and says, anytime 2 or more customers are making the exact same request, not just a pack objects on a particular repository, but they want exactly the same versions of exactly the same files from the repository, we now cache that on the fly. And so the 500 requests that come in from the deploy servers or the continuous integration servers, we can compact those down to basically 1. We still have to send the file out 500 times, but we only do the CPU work. We only consume the memory for 1. About 11% of our traffic can be served from the Lariat cache. Now, 11% sounds like a really terrible hit rate. Anybody who knows anything about caches, like disk caches and CPU caches, they're in the high 90s if you've got a good hit rate. But with Lariat, 11% is great, because it's hitting the 11% that are the most severe performance problems for the file servers. And here it is in practice. I love this graph right here. This is a graph. In green is CPU attributable to one particular repository, and in red is the number of requests per minute for that repository. And so you can see we've got 2,000 requests a minute. We've got people asking for 30 hits a second, 30 fetches a second for that repository, and they're consuming about 20 cores of CPU. Our file servers only have 32. So if you're taking 20, you're squeezing out a lot of other traffic. This is bad. And this is with Gitmon in place. Gitmon is struggling to keep this repository under control. Anybody want to guess where we turned on Lariat? I'm going to say right here. And there are 2 things that change to the right of that. Most obviously, the CPU numbers go from basically 20 cores to 1 core. And that's fine. If a deploy to hundreds of servers takes 1 core, we're fine with that. The other more subtle thing that happens on the right here is there's more of the red. So now they're able to get more requests through more quickly. So not only are we protecting the rest of the users on the server, we're now delivering much better service. We're responding faster to the user who was causing the trouble in the first place. On the right here, this graph is Lariat herd sizes. And so, I mean, it's tough to read the y-axis labels, but that goes up to 16,000. Sometimes we get 16,000 identical requests all at the same time. I don't even know what repository. That's crazy. But now we're doing it for the CPU cost of 1 hit. Final thing I'm going to talk about today is a new system that we built, that we're debuting today publicly, called DGit. And this is to deal with failure. So servers fail, that's reality. If you're running one Git server, you can basically pretend that it doesn't fail, because maybe the mean time to failure is a couple of years. And when it happens, you have some downtime, you apologize to your users, you go to the backup tapes, whatever. When you have a handful of servers, you can spend a bunch of extra money on things like RAID and redundant power supplies, redundant networking, professionally managed hosting centers, and you can kind of pretend that failure doesn't exist. You can rely on things like RAID and server failover when the failures happen. But the more servers you get, there's a linear or worse increase in your individual server failure rate. And so at the bottom, this is a status tweet. This is from a few months ago. It's from December. This is what it looks like when a file server crashes at GitHub. The server didn't fail permanently. It was kernel panic or something. We tweet that we have an issue affecting a small number of repositories. Often that's GitHub code speak for a file server is down. And then 25 minutes later, everything is operating normally. So the million repositories on that server for 25 minutes, sorry. That's what we're fixing here today with DGit. And the reason it takes so long, servers take a long time to reboot. We also have humans in the loop to notice the failure, to manually fail over to the hot spare for that server, to verify that everything's all right, and then eventually to tweet that everything's okay. Our goal in DGit, which we have succeeded at, is to store 3 copies of every repository on different servers with very different failure patterns. So put them in different racks, put them in different availability zones, and make sure that no one server is ever solely responsible for anything. It's okay for a server to crash. It's generally okay for several servers to crash. It's okay for a whole rack to crash. And it doesn't take 25 minutes, and we don't have to tweet to our status account that anything's down. So this is DGit. We've overhauled our storage cluster and to ensure that every operation can run in at least 3 different places, and specifically 3 different places that are unlikely to fail at the same time. Server failures now have no user visible impact. That's a tough thing to test, though, right? I mean, how do you unit test kernel panics? Greg said he can't. We can't either. So no, we test with sudo reboot. We log into production servers, we do sudo reboot. I gave an internal talk at GitHub where I just did a demo. One of my slides was, wait, I'm going to switch to a terminal and reboot the server. And it worked. And another good test, rm-rf. So the DGit has repair protocols. DGit notices when a repository has stopped working, and of course has 2 other copies, is able to synchronize it using, guess what? Using Git. So DGit is distributed Git, but Git is already distributed. We're really just keeping 3 standalone Git repositories and using Git to move to move objects from one to another. Here's how that looks. So anytime you push something now, or any other write, a web edit, a merge, whatever, it goes to a proxy, and that goes to all the file servers for that particular repository. I said there are at least 3. Here's how it gets to those 3. It gets to all 3 at the same time. And the push or the write only succeeds if 2 of them say yes, because 2 is a majority of 3. If we've got it on 5, then 3 need to say yes, and so on. When you've got a fetch or a read or anything else, just building a web page for the repository, it only needs to go to one of the file servers. And there's really fast failover if something is wrong with that file server. If you can't connect to the file, if you have connection refused, connection timed out, any sort of unexpected error, it just goes to this one instead, or it goes to that one instead. And there's a lot of flexibility in choosing which file server is available, which file server is not overloaded, which file server is close to a customer. Reads got a lot better when we started doing our replication at the application level. We started explicitly knowing which file servers any repository was on. With this, writes tolerate single failures, because I said we need 2 yeses. Reads tolerate double failures. It's very rare to get double failures in 2 different racks or 2 different availability zones. But if you do, you mark that server offline permanently. DGit sees that there are only 2 copies. It makes a 3rd copy. It's all automatic at this point. Here's how it looks from the administrator's point of view. The infrastructure team loves DGit because it's failure tolerant. So now we don't have to worry about single file servers going down. When we have to reboot one for maintenance, we can. Our old file servers had uptime of like 2 years. That's no longer necessary or useful. It's self-healing. If anything is broken in one of the 3 copies of a repository, Git fixes it. And it's self-balancing. So we want to make sure that each server is equally full and each server is equally busy. And moving repositories around ensures that they're equally full. Moving read load around ensures that they're equally busy. This is the rollout. So as of this morning, about 60% of repositories are in DGit. So Any of you who are GitHub customers are benefiting from this already. Nearly 100% of gists are already in DGit. It works. If you haven't noticed, that means that it works. One quick case study. I have blurred out the name of the repository to protect the guilty. For code, I'm going to call them CocoaPods/specs because that's their name. You might have seen this Hacker News or the trade press a couple weeks ago. It's a big repository. They've got 10,000 unique clients. And normally we have a lot of repositories with 10,000 unique clients, but they were doing shallow fetches. And anybody who's really geeky into Git, you can't reuse your deltas. So a shallow fetch, instead of taking 1 second of CPU time, takes 30 to 60 seconds of CPU time, and there's no easy way to optimize that. So we had busy servers. The CocoaPods users complained to support. Nobody else did, because Gitmon works. Gitmon was effectively limiting that repository to pegging 5 CPU cores constantly night and day. We turned on detailed logging. That's how we found out they were doing shallow fetches. We encouraged the repository owners to stop doing shallow fetches, but there's some turnaround time on that. And so in the meantime, we moved this one to DGit. So you saw the rollout ramp. This goes back about 3 months. We moved CocoaPods to DGit. Suddenly it's got 3 servers instead of 1. And so it's got 3 times the capacity. And we stopped having to quota anything. So now this crazy amount of load, this is just going through at full speed. So when you've got 3 servers, it's okay to dedicate 5 cores constantly to them. Summary here. So when you run the biggest Git host in the world, you see high traffic. It's spiky traffic. And I don't just mean that it's high after lunch on the East Coast or whatever. I mean, we get deploys where hundreds or even thousands of servers ask for the same repo at the same time. Those are serious hotspots. We get some corner cases, busy, deep repositories. When you got more servers, you got more problems. Failure rate goes up more than linearly, so you have to write software to deal with failure. And our answers, as I talked about, we monitor everything. We log every single Git operation. We have an established workflow with Git core developers who can make Git faster for us. We cache everything. I introduced Lariat today. We do adaptive and predictive load management. That's Gitmon. So we prioritize light traffic over heavy traffic, effectively. And finally, we have moved replication from being at the disk level and the server level to being at the application level so that we're keeping 3 copies of everything. We have hot spares of everything. And that's it. Thank you for your attention. I haven't left much time for questions, but I'd love to catch up afterwards. And you can find the blog post and the Wired article if you want to learn more about DGit.
Thank you, sir.